So Newton comes by, right, after Galileo and Kepler and Copernicus, right? And he decided to investigate what causes objects to go around a large, massive body, such as like a Halley's Comet going around the sun once every like 75 years, right? And what causes Earth or any other planets basically to go around the sun, right? Newton figured there had to be some kind of attractive force that's causing that to happen, okay? So back in 1666, there was like a outbreak of bubonic plague again in London, right? So they were in lockdown. They closed universities and all the institutions, and he had to retreat back to his aunt's farm, an orchard actually, apple orchard, right? And there, at age of around like 26, right, or 25, he basically did some incredible work during that time. Okay, so back in 1666, using mathematics, Newton showed that for a planet to move in an elliptical path, right, Newton proposed there had to be some kind of a force, right, between the two objects and the distance between the center of the planet and the center of the sun. Okay, so he measured the distance as sun as a particle, like point particle, and planet as a point particle. So the thickness of the sun really didn't matter. Okay, and then Aiden, do you have a question?
Yeah, I was just wondering, are you sharing your screen? Because I can't see anything.
Oh my God! Thank you. Is that better?
Yeah.
Thanks, Aiden. All right. All right. So he figured, okay, there has to be some kind of force between the planets. Now, you don't have to learn how to derive this. I'm just going to show you one so you could see how it had developed, but you don't have to like derive this again. But I just don't like to throw an equation up there and say, memorize this and use it. No, I just want to see so that we can sort of understand how Newton thought about all this in his head to figure out this force of gravity. Okay. So the force has to be proportional to this little fishy thing is actually meant proportional to, right? Inverse square of the distance. So he had some intuition saying that this force and the distance of separation had to be inversely proportional to the square of the separation. Okay, so he recognizing that said, okay, well, sum of all forces equal to ma. Okay, and the force for the planet to sun has to equal to the mass of the planet times the acceleration of that planet, right? So he said the acceleration of the planet has to be this basically is circular motion, right? The acceleration for the circular motion, okay? And the c cubed is basically, and t squared is Kepler's third law, right? Times that by 1 over distance squared, sine of phi, right? Don't ask me how he got this. I could derive it for you, but you don't really need to know it. But he just basically got to this point, but he knew that this right here has to be constant. And according to Kepler's third law, right? C cubed over period squared has to be constant. Okay? 4 is constant, pi squared is constant, right? So this whole thing is constant right here. Okay? So looking at the picture below, right, you can see that the total acceleration is given by a is equal to ap over sine of phi. Therefore, the sine of phi and this sine of phi will cancel out. Okay, so it simplifies to this. Okay, now since force is equal to mass times acceleration, So the mass of the planet times this acceleration, right, is what the force is causing the planet to go around the sun. So the only thing he did was basically he multiplied this by mass, the mass of the planet. Now again, you don't have to memorize all this. I'm just showing you how we got there. Okay. So the mass of the planet divide by the distance squared times this constant. This is a constant right here. Right? C cubed over t squared is constant universally. And 4 pi squared is also a constant. So this big constant right here. So he knew that this, he just represented as big K, like constant K. So force is equal to, right, this constant times mass of the planet divided by the distance squared. Okay? So since the constant right here, he knew that this has to be same for all planets. So the mass of the planet can change, and this distance between the planet and the sun can change, right? But this constant has to remain the same. And since he knew this force between the planet and the sun has to be same as the force between the sun and the planet, he knew the mass of the sun had to be involved with this K. This K had to be some other constant times the mass of the sun. So he said, all right, then this G times the mass of the sun times the mass of the planet divided by the distance squared, okay, has to be the force that's causing this planet to go around the sun. Brilliant, actually, right? Brilliant. He knew this K is equal to 1.33 times 10 to the 20th, right? Meters cubed over second squared. He knew this. But what he did not know was, he didn't know the mass of the sun, or he did not know the mass of this constant G. He did not know this, right? But he knew that this had to be this. So he couldn't figure out what that G was, and he couldn't figure out what this mass of the sun was. But later on, okay, later on, Cavendish, Lord Henry Cavendish, did this experiment, okay, to figure out what that G was later. And this after Newton passed, right? After Newton died, that was basically what Lord Cavendish did, okay? That's about like 70 years later, Newton's death, he figured this G out. So how did he do this? Well, what Cavendish did was he actually had to work this in a completely isolated place. So he like basically set this apparatus up in this huge like atrium in this like botanical garden, right? Well, he was Lord, so he was very rich, you know, he had all the money in the world basically. So he actually hung this rod with two masses at the end, okay? And on that rod, he placed a mirror, and when the light shines on that mirror, it would reflect back to the other side of the room, okay? And then he stabilized it as best he can, and then he brought in big, giant, like lead balls near it, and he noticed there was some kind of an attraction between them. And when the attraction happened, this mirror twisted, which will make the beam hit a different place, okay? And then he reversed it. So instead of putting it here, then he actually put this thing on the other side, see how that much is attracted. And he also noticed that this thing was being attracted as so to a different place. Therefore, using this knowledge, he actually calculated this G. This G is universal gravitation constant. Okay? So, universal gravitation gravitational constant. As far as Newtonian physics, this value is universal. Okay, it happens between every two masses in this universe that we know. Okay, now of course when you get to like black holes and white holes and other stuff, this does break down once you go past the event horizon. But for now, this is good enough. Okay, so once he figured that out, Newton's universal law was complete. Okay, so Newton assumed that his law should work for any two objects. That's why it's universal, not just planets. So it could work between planet and the moon, or the planet and the artificial satellite. It could pretty much work just about any two masses. Okay. Now, how did he come about that there has to be some kind of a force that's causing it to orbit around? People were, skeptical because how could this something, one object, attract another object, and you could just call it anything you want, like gravity, right? That's fake science, right? But Newton actually had a brilliant insight, and he explained it beautifully to people who are skeptical. Okay, so he said, imagine Earth, right? Imagine Earth. It's a little lopsided, sorry. And on that Earth, you build this huge pyramid. This pyramid is bigger than Mount Everest, right? So it's taller than Mount Everest, which means it's the tallest structure in the world. And on that pyramid, let's say you were to place a cannon on top of that planet. And it's a big cannon, right? It's a big cannon. And you decide to fire a cannon, right? Horizontally, right? So fire a cannon horizontally. Right? Horizontally. That means if there were no gravity, this cannonball, when it's fired, right, would go straight across like this without going back to the Earth. If there were no gravity, right? However, we all know that this cannonball will fall back to the Earth. When we fire this horizontally, it will fall back down like so. And there goes the neighborhood, right? So this is with gravity, right? So this is with gravity. Right? Well, he decided to load up this cannonball with more gunpowder and fire it with higher velocity. So what happens? Well, it's going to go even further, but maybe it'll like go to a different country and land on the different country, right? So he said, you know what? If we even put more gunpowder in there and fire it with even greater speed, what's going to happen? It may even go like halfway around the Earth before like it, comes back down and land on the ground. Like there goes the penguins, right? So he said, you know what? There has to be like one single velocity that is perfectly calculated that can make this cannonball fire with such a speed that it actually fires, and it goes and it falls back down to the earth. And as it falls back down towards the earth, guess what? The earth itself curves away from its fall, and it just continues to fall and fall forever. And if you remove that cannon, guess what? It'll just keep falling forever. That's what the moon is doing around the earth. And he basically explained this so beautifully, people were actually convinced. Right? It's a thought experiment, obviously. And that's exactly how, right, the cannonball actually goes around the earth forever, falling and falling and falling forever. All right? So if you were to think about how that happens, instead of using a cannon and a cannonball, right? What if we were to use, I don't know, maybe a rocket, right? If we make a rocket ship and then we blast it off, right? We blast it off. So when you shoot a rocket, you don't just shoot it straight up. It actually goes up and then it actually does this. And when it reaches a certain altitude, all you have to do is just release the satellite at a certain speed. And this satellite will just stay in orbit forever, just like the moon. Well, Newton basically discovered this around 17 20s, right? And we haven't really implemented this until the Soviet Union back in 1950s, right? So after 200 years after Newton predicted this, Soviet Union launched this artificial satellite called Sputnik. The Sputnik was just going around in a circle around the earth beeping, and America, United States, just freaked out. Okay, just freaked out. Why? Well, if this thing is orbiting around, we don't know what's in there. Second, when this thing orbits around, and what if you slow this thing down? What's going to happen? It's going to fall back to Earth. And you can pretty much calculate where you should slow it down to make it fall back down towards the Earth at anywhere you want. So they have capability of reaching any country on this surface of this Earth. That's when United States decided to teach physics to all students, right? And that pretty much revolutionized artificial satellite technology. All right? So, universal gravitation is very important to us. So let's analyze this equation right here. Let's analyze that equation, okay? What do they all mean? First, F, this F, and I'm going to make this F with subscript big G, not small g, right? The weight is, mg, which is small g, right? That is universal force, gravitational force, right? Between two masses. It doesn't work with more than two. You have to do just two at a time. Okay? Gravitation force is attractive force, right? It never repels. Okay? What is G? G is universal gravitational constant. Oops. And it has a value of 6.67 times 10 to the negative 11th, okay, newtons times meter squared per kilogram squared. And this value will not change. It will always be the same no matter where you are or what two bodies you're working with. Okay? M1 is mass 1. This could be the sun, right? Or planet, right? Now, if the planet's going around the sun, you can make the mass 1 the sun, right? Right? Or the, whatever, a star, right? Etc. You could call this one central mass, right? Central mass, which means whatever an object is going around that, like for example, if moon is going around the planet, then planet is the central mass. If the planet's going around the sun is the central mass, right? So the mass 1 is the central mass. Mass 2 is mass that is orbiting, right? Or the second mass that you're comparing. Now, it doesn't have to orbit. It could be just two masses, right? You're just looking at it at instant when two masses are there, right? So we don't have to think about it's always orbiting, but it's nice to know that when we're talking about orbiting or satellite motion and planetary motion, it's not that bad, right? You should know it as this way. Okay. And d square is square of mean radius, okay? Square of the mean radius of the circular orbit. Okay. Or simply the square of the separation between the two masses, right? Oops. Between the two masses. The important thing is that distance d must be measured from center to center, right? So measure from center to center. That means if you're measuring from distance from the Earth to the moon, it has to be measured from the center of the Earth to the center of the moon, right? So this distance is d. Okay? Hopefully that's understood. So if you're thinking about like a distance of orbit of, let's say, artificial satellite and Earth, you have to actually use the radius of the Earth plus the altitude of the satellite to get the d. Okay? So maybe I could write that down. So this is the radius of the Earth plus this is the altitude of the satellite, right? That is equal to d. So you have to add radius of the Earth plus the altitude. All right?
Mr. Kim, I think class is over.
No way. Oh. All right. Have a nice day, I guess. Is it? What time is it? What time is it supposed to be over?
I think it ended at 11.
No. I forgot we had 2 hour delay today, right? Okay. Have a wonderful day, everybody. Thank you for coming. All right, enjoy the snow.
Thank you.
Thank you, Mr.
All right.